In section 7.4, we'll look at conservative forces and potential energy. Our goals here are to link force and potential energy using integrals and derivatives. So we're going to see what that link is, and then use these connections with springs and gravitational forces to solve some problems. Now consider a falling book. If we had a book up here, and this book was falling downwards, it's starting at some initial height above ground, ending at some final height here. If we looked at the work done by gravity, the work done by gravity would basically be sucking potential energy out of the system, because it's going to start with a high potential energy up here. If we called potential energy equal to 0, or the reference level to be down here, maybe at the floor, it would start with a high potential energy up here at the bottom, and it would end with a very low potential energy once it got down to the ground. So basically what we're saying is that the work done on the book by gravity is going to be this negative delta U, or this mgyi minus an mgyf, or loss of potential energy. This is the essence of a conservative force. The work done, it only depends on your initial and your final values. So it doesn't matter how the book gets down to the ground, it just matters where did the book start and where did the book end. Now, a function like we're going to create here can't exist for a non-conservative force because work depends on the path followed. And the function that we have up here can't exist for a non-conservative force because it matters how you got from point A to point B, or yi to yf. Now, when we look at these conservative forces, we can develop a mathematical equation for conservative forces from this definition of work. So we'll begin with the most basic mathematical expression for work being the integral of that force. Now, since we said that this work was equal to this negative delta U, that means that the integral of the force with respect to position can be set equal to this negative delta U, or a negative UF plus a UI. Now, simply rearranging this and pulling this over to this side and this over to the other side, we get UF equal to a negative integral from xi to xf of f of x dx plus the initial potential energy. Really, all we're saying here is that an equation for potential energy can be found based off of the equation for force. So if you know how force affects an object, you can take the negative integral of that object with respect to position and actually find an equation for the potential energy of that object for various positions along its motion. So this equation allows us to find the potential energy function, knowing that force function for a conservative force. The initial potential energy that you're adding on here is oftentimes equal to 0, but it really doesn't matter what that is, because really we're looking for the change or the difference in the potential energy that's actually useful or sort of matters to us. That u sub I is just going to sort of shift this function in one direction or another. So let's look at a couple of examples with some forces that we know what our answers should be. Let's look at the potential energy function for a spring that would obey Hooke's law. Now, what we just said is that we could find that potential energy function based off of integrating the function for force with respect to position. So that's exactly what we're doing here. We're going to take the negative integral from some initial to final positions of this force for this spring and integrate the force of a spring, which again, using Hooke's law, is a negative kx. We'll integrate with respect to x as our variable. Now, when we do that, we can see that this negative and this negative sort of just cancel each other out, and we would integrate kx, giving us a 1/2 kx squared. Plug in the values of xf minus the xi, and we get 1/2 kxf squared minus 1/2 kxi squared, again plus whatever initial potential energy we may have been starting with. Now, if we say that the initial position of this spring was in equilibrium, then xi is simply going to be a 0 position. And if we say that the initial potential energy at that position is also a 0, what we really end up with is just the potential energy of a spring being a 1/2 kx squared. We already knew that this should be our final answer since we've been using this in other parts of Chapter 7 as we've been analyzing energy problems. So here we see that, in fact, this UF equaling the negative integral of force does work for a function that we knew what that answer should be, or it checks out for springs. Now, if we know that we could find the potential energy function from a force function, does it work the other way around? Could we find a force function if we knew the function for potential energy? And that answer is absolutely yes. If we say that the potential energy is equal to the negative integral of the force, we can simply sort of undo this function or work backwards the other way to find an equation for force instead. And of course, the opposite of an integral is going to be a derivative. So rather than integrating force to find potential energy, we could take the derivative of potential energy in order to find a force. And that's where we come up with this equation here. That force is now going to be equal to a negative derivative of potential energy, again with respect to position. So let's again make sure that this actually checks out. Let's take a potential energy function that we know. We know that the gravitational potential energy of something as it sits some height above Earth is going to be equal to an mgy. Now if we take the negative derivative of this with respect to y, we would lower that power of y, which is a 1 right now. We'd lower that power by 1 so that it now becomes a 0. And really when we stick that negative in there, we just get a negative mg. Again, we know that this makes sense and we know that that should be the case since the force of gravity is a negative mg.